Hello everyone, my name is Raoul Buchang. I'm the CTO of HQLAx. I'm here with Mario Schlipf, who is our lead engineer, and a number of other colleagues here. There's quite a few faces. And I want to talk a bit about what we did to make HQLAx go live on Corda and its integration with existing financial markets infrastructure. It probably helps if I explain briefly what HQLAx is about. And let me start with the acronym. The acronym HQLA means high quality liquid assets. That's just a subclass of securities. It's securities that are easy to liquidate. And banks care about those because they need to have reserves for regulatory reasons. And HQLA, so that particular class of securities, can go into those reserves. So you can use them. They count toward a bank's reserves. So they like to have them. They need to have them. And that's why you have trading in those securities. Securities are not something that you typically hold in your pocket. They're stored at safekeeping organizations, specialized organizations that are called custodians. And we'll talk a little bit about them too. Now, so these securities are commonly traded in, and one particular type of transaction that we look at is called a securities lending transaction. And it's really just me lending securities to Mario, who's a bank, and he wants to have some HQLA. I have some. And so I lend it to him for some period of time, for as long as he needs it, and then he returns it to me. But it's a big amount. He wants 100 million of government bonds. So I want some collateral in return in case he goes bankrupt. I'll have the collateral. And the collateral can come in different forms and shapes. It can be cash, but we're looking at the case where it's the collateral itself is also securities. And that could be just stock or equity. So we basically have a swap of securities. I lend the securities and I get the collateral in return. We do this for a period of time, both holding our stuff, and then at the end of that period of time, the swap's reversed, the securities return, and the collateral returns. That's the basic transaction. It's pretty simple. It's illustrated on the right-hand side. We do a trade. We agree on what we want to swap. It gets confirmed, and then at some point in the future, it opens, and the securities need to move from me to Mario, and his collateral needs to move from him to me. That's really it. Now, things are nice if both are securities and equity and if everything is stored at the same safekeeping organization, the same custodian. It's all nice and simple. We send instructions to the same place and tell it, this is what we're going to do. We need you to change the ownership on these securities on that date. We'll do it for this amount of time, and when the loan expires, we'll send you instructions again to reverse things. And the custodian, it has all the accounts, both for me and for Mario. It can do an atomic swap, and it's all great. Life is simple and nice. Now, what HQLAx is about is really the situation where the settlement landscape, where these transfers happen, is fragmented, and where my securities live in another place than Mario's securities, and they can be in different custodians. And then these transfers that need to happen when the trade opens and when it closes are not so simple anymore. They're painful and potentially risky. So imagine that I would instruct my custodian to just transfer the securities to Mario's custodian. And then Mario sort of forgets to instruct the transfer of the collateral. That would be a little painful. Or Mario goes bankrupt. Then I've send off my securities, 100 million's worth, and they're gone. And that's not nice. So that's we don't want that. So the HQLAx platform is looking into solving this issue. And the basic idea is pretty simple. It's don't do that. Just don't move the securities and keep it a bit simpler. The crux of the solution is really to well, the key of the solution is to record the ownership on a Corda ledger and use that as a source of truth for who owns the securities at which point in time. So that's illustrated here, where you can see a trading system on top. Then, below that we have the digital registry of who owns what, and then at the very bottom you can see the custodians. We start out in a situation where, the purple securities on the right-hand side are held on the right-hand side there, but they're stationary. They live at that custodian on the left-hand side, and the white securities are held by the custodian on the right-hand side. And when the trade opens, something like, oops, does that work here? Can you play that? Yeah, a swap happens, but the swap only happens at the Corda level, and then when the trade closes, things go back. But there is no movement of the securities across the custodians. And this is really the key idea, and it has a number of advantages. So first, we can do this relatively quickly, intraday if needed, and it's atomic, so there's no risky one-way transfers. So let me talk a little bit about how to make that work in the real world. We started out as an R3 project, incubator project. A POC was developed with the banks you see listed here. My former colleague Matthijs did a lot of work on that POC. And that was really successful, and as a result, a company was spun up to turn it into a product. And that happened, and that product is basically a Corda app initially with a number of custom UIs, and was used to do a first live trade of this nature, basically a securities lending transaction, as I just described, between a number of banks. But if you look at that system at the time, it had the Corda app in place, but it had a number of custom UIs, and there was no integration with a real marketplace. We had basically a demo marketplace, and similarly, we had an API to the custodian, but there was still a fair bit. There's no real integration with the underlying landscape. But we did prove the concept, and there was a real trade, including all the legal work that comes with that, and that's significant. So sometime later, that resulted in a major investment from Deutsche Börse Group, and they became a strategic partner of HQLAx and brought with them a number of key components. So one of those components is a trading place, a trading exchange that we're now integrating with and connecting to. And similarly, at the other end, at the custodian end, we're now integrating with a number of major players in that area. So Clearstream, Euroclear, and JP Morgan is next.
All right. So let's have a brief look at how the HQLAx Corda network looks like. So for every participant that we have in our platform, we basically run a separate Corda node. We have different types of roles in our network. So we have trader nodes, which are basically the banks or financial institutions that want to trade with each other. Then we have a Eurex node, which connects to the existing Eurex repo trading system. So we interconnect with an existing API that is used by other participants as well. And on the other side, we have the TTP node, which connects to all the custodians through our trusted third party. And our main type of state we have on the ledger is basically the trade itself. And we receive those trades from the Eurex system by requests. And these requests contain information about the parties that want to trade with each other, about the securities, the amounts of the securities, and where the securities are held, at which custodians. And while the trade goes through its life cycle, so opening and closing, we also need to interact with these outside parties to inform them about ownership changes, etc. So apart from developing the Corda itself, we actually spend a fair bit amount of time integrating into these existing systems. And since this talk is about integrating into a financial markets infrastructure, I want to spend the next couple of minutes talking about a few of these architectural designs that we needed to implement to make this work. So the first thing is about Corda's interface from outside. So as I said, we connect to Eurex, and Eurex provides an API that runs over message queues, so AMQP, which is a reliable protocol. It gives us certain types of guarantees, like at least once delivery or transactions, so you can make sure that you either fully commit or roll back your transactions. And internally, Corda uses the same protocol. So for node-to-node communication, Corda uses also AMQP. However, for outside communication, Corda uses RPC. And the problem is that RPC is not as reliable as AMQP. So you have to, so basically when you do a request, anything can go wrong during that request. So the request can time out, or one of the applications can crash that is involved in either the requester or the Corda node. And you might end up in a state where you don't know if your request was processed or if you should perform that request again. And so if we receive a trade from Eurex about $1 billion, then we kind of want to make sure that this trade is executed exactly once. So what we had to build was a application-specific exactly once execution on top of the RPC interface of Corda. And the way we solved it, it sounds quite easy. So for every request that we receive from outside the Corda node, we require the request to have a unique request ID. And before we execute that request, the first thing we do is we look up in a special lead application table that we've built whether we've seen that request before. And if we've seen that request before, we don't really execute it, but instead we will just return the result of the previous execution, which we also store in that DB application table. And then similarly, if the request is new to us, we store the request ID, execute the request, and then return the result. Now that sounds quite easy, but the devil is in the detail here. And if you want to get this right, you have to think about edge cases like, you know you've seen that request before, but the execution of the first request might not be finished yet. So you have to wait for the first execution to finish. Also, you need to implement garbage collection, so your database table doesn't fill up with older requests. And this only works if your result types are not too complex, because if they're too complex, again, you end up filling up your table space quite fast. Now, the second thing is basically communication the other way around. So as I said before, our trades, they go through certain life cycle steps. They open, they mature. And we wanted to have a way of informing the outside systems like Eurex or the custodian side about these changes. And again, this had to be reliable, so we need to make sure that we don't lose any events. The events have to be delivered in the correct order. And for those of you who develop their own Corda apps, you might think about the track by function of the vault. So the vault provides a way for outside applications to subscribe to any state change. And the way it does that is it returns you first a snapshot of all the state changes that happened in the past, and it will inform the subscriber about future updates when it happens. The problem with that function is that if the subscriber crashes and needs to resubscribe, you get this snapshot again, and you don't know where you should continue processing it unless you add some persistency outside of the Corda node. But because we didn't want to do that, what we've actually done is we built our own event queue inside of Corda. So again, we have a separate database table, and the first thing we're doing is we subscribe to the updates of the vault. It's called raw updates, that function. And this update runs in the same database transaction as the vault update itself. So if we assume that the vault update is resilient to any crashes, then we can assume that our building up of the event queue is also resilient. And then what outside subscribers can do is we provide a flow that subscribers can use to get the very next event of that queue. And then the subscriber can process that event. So for instance, we process it and send it back to Eurex. And after you finish processing it, you acknowledge the event with a separate flow. Now, if the subscriber crashes, it might still be happen that the very next event is processed twice. But in our specific use case, that was acceptable. So we can process the very latest event twice. So that worked for us. And special kudos go to Peter Rutgers at ING, who actually implemented a very large part of that one.
So in summary, the integration with these across these RPC layers was quite tricky and time-consuming. We're basically building application-level reliability protocols. It's been a recurring theme of our integration efforts. This is just a deep dive on one aspect. There's a couple of other issues here: scheduling, archiving, business network management, firewalling. These are all issues that come up when you go into production. R3 has been very supportive in that area, in a number of issues that had to be addressed as we together go into production. We are now in production with the system. We are technically ready for live trades. We hope to have them next month. We are onboarding customers and banks. They are actively testing in a end-to-end test environment. You can see us here today and tomorrow, or you can visit our website. And I think I'll have to stop there.
Yeah.
Sorry for running late.
No, that's okay. No, you're exactly on time, but we do have one question. I think you may have just actually answered it here, because it was asking how many live transactions per day, week, and month. And I think they're actually starting next month, you just said. So.
Yeah, so
Okay, cool. As the guys just said, they're here for the next 2 days, so you can contact them via the app. You can meet them outside, and I believe you're actually presenting again with some customers tomorrow. So if
Guido's on the panel tomorrow.
So thank you all for coming. I've just seen on the messaging on the app that lunch is now served, so I think that's probably where everyone's going next, but there is another session in here in 10 minutes if you're interested. Thank you.
Thank you.